Calculate the number of moles of solute present in each of the following aqueous solutions. All right, A. They give us a 600 milliliter, 0.25 molar strontium bromide solution. All right, so if we multiply liters by moles per liter, right, so convert milliliters to liters, multiply it by the molarity, that'll give me moles of the solute. B. They give us 86.4 grams of a 0.18 molal solution. All right, so if I have grams of my molal solution and I convert it to kilograms of my molal solution, then I can use the molality to go from kilograms of solvent to moles of solute. I'll tell you what, whoever wrote this question, it was a bad one. Doesn't make sense. They give me grams of solution. I need grams of the solvent if I want to get to kilograms of the solvent and then cancel kilograms of the solvent. So shame on whoever wrote this. This isn't a good question. This is how you would do it, but it's a bad question. We'll skip it on the test. C. We have 124 grams of solution. Okay. That is 6.45% glucose by mass. All right, well, this one's straightforward, right? Turn that percentage into a fraction. If I multiply the fraction by the total mass, I'll get just the mass of the glucose, and then I can use the molar mass to get to moles. That one's a good question. B was not a good question. 65. Calculate the vapor pressure of water above a solution prepared by adding 22.5 grams of lactose to 200 grams of water at 338 Kelvin. Vapor pressure data for water is given in Appendix B. Okay. What we're getting into with this problem are colligative properties. All right, so you're going to have to bear with me. I'm going to do a little lesson on colligative properties. For example, a liquid at any temperature, some of the particles in that liquid have enough kinetic energy to escape into the gas phase. This is what is called vapor pressure. If I add to the solvents a non-volatile solute, meaning a solute that doesn't have a vapor pressure, those solute particles occupy surface sites and lower the vapor pressure. Now, notice I put sodium chloride in the one container and sugar in the other. It doesn't matter what kind of particle it is. It only matters how many particles. So with sodium chloride, you're getting twice the vapor pressure lowering effect because you're getting twice the number of particles. So 6 NaCl's give you 12 particles, whereas 6 sugars only give you 6 particles, so less of an effect. So that's what colligative properties are about, right? It's about particles affecting things like vapor pressure of your solution. So if I have the pure solvent, right, has a boiling point or a vapor pressure at 100 degrees Celsius, if I add a solute, a non-volatile solute to the solvent, I lower the vapor pressure. I no longer have a vapor pressure at 100 degrees Celsius of 760 atmospheres. It's less, 740, 730, whatever. And it makes it harder to boil. So if you're lowering the vapor pressure, it means it's harder to get into the gas phase. That means you got to raise the temperature if you want to get it to boil at 1 atmosphere pressure. So that's boiling point elevation. Along with that, you're interfering with the solid liquid interface and you're making it harder to freeze. So all of a sudden it freezes at lower temperatures. This is called freezing point depression. And these are 3 of the colligative properties we look at with solutions. All right, so let's get to the problem. I had to go to a table, right? What I'm going to leverage here is this equation. Pressure of the vapor is going to be equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. So what we needed this data table for is to get what the pure vapor pressure of water is at that particular temperature. So if I have 22.5 grams of lactose, we use the molar mass to get to moles. They gave me grams of water. I use molar mass of water to get to moles of water. And then to get to mole fraction, I take total moles, moles of lactose plus moles of water, and divide it into moles of water. I want the mole fraction of the solvent. All right, so most of this solution is the solvent, right? So I usually have very high mole fractions for the solvent. Okay, now I get the mole fraction of the solvent. I go to the table to get the pure vapor pressure of water at 65 degrees Celsius, which is the same as 338 Kelvin. And now I can multiply the mole fraction by the pure vapor pressure of the solvent and get what the adjusted vapor pressure is for the solution. So that's how this works. B, calculate the mass of propylene glycol that must be added to 0.34 kilograms of water to reduce the vapor pressure by 2.88 torr at 40 degrees Celsius. All right, so we're leveraging this equation again. Now, in this case, they told us what the adjusted vapor pressure is, right? So if I knew what the vapor pressure of the solvent was at 40 degrees Celsius, I could figure out what the mole fraction of the solvent is. So I look up at 40 degrees Celsius what the vapor pressure of the pure water is, plug that in and multiply it by the mole fraction, set it equal to the adjusted vapor pressure, right? The vapor pressure has gone down by 2.88 torr. So I can solve for the mole fraction. So the mole fraction is the moles of the solvent, all right, they gave us grams of water, so we can find moles of water, over total moles. Moles of water plus moles of propylene glycol, which I'm going to call Z, just for room. All right, so we're solving for Z, the moles of propylene glycol. So if I multiply both sides by 18.9 plus Z, I get 0.948 times 18.9 times Z. Gives me this. I then can solve for Z, right? Subtract 17.86 from both sides, divide both sides by 0.948, and I get how many moles of propylene glycol I have. All right, so once I have moles of propylene glycol, it's just using the molar mass of propylene glycol to calculate grams of propylene glycol. And that's how you do this problem. Why does a 0.1 molal aqueous solution of sodium chloride have a higher boiling point than a 0.1 molal aqueous solution of sugar? It's about particles. 2 moles of particles per mole of sodium chloride, so you're getting twice the colligative effect. So it doesn't matter what kind of particle it is, it just matters how many particles you put in. So if I put in 1 mole of, or if I have a 0.1 molar solution of sodium chloride, actually I have a 0.2 molal solution of particles. So twice the number of particles occupying surface sites, less vapor pressure, harder to boil. Twice the colligative effect. All right, so B, calculate the boiling point of each solution. All right, so we're leveraging this equation, right? Delta T is equal to the Van Hoff factor times the Kb value times the molality, right? So we're equating molality to the raising of the boiling point. So I need moles of solute per kilogram of solvent. They gave me the molality. I don't need anything, right? They gave me the molality. I have to look up what the Kb value is for water. Multiply the Kb value of water by the molality. Molality cancels. Since I get 2 moles of particle for every mole of sodium chloride, I'm getting twice the colligative effect. All right, so I solve for delta T. I add that to whatever my normal boiling point is, and this gives me how much the boiling point's been raised. All right, so with this very dilute solution, I didn't get too much of a raise in boiling point. It's not that much harder to boil with a 0.1 molal solution of sodium chloride. So let's see what it is for sugar. All right, so instead of having a Van Hoff factor of 2, I only have a Van Hoff factor of 1. So I'm not having twice the colligative effect. I'm having a straight for every 0.1 molal. I'm getting a certain raising of the boiling point. So again, half the colligative effect. So 0.051 plus 100 degrees rounds off to 100.1 degrees Celsius. So the fact that these are such dilute solutions, you're really not emphasizing the point between getting twice the number of particles with sodium chloride because the molalities are so low. All right, C. The experimental boiling point of sodium chloride solution is lower than that calculated. Assuming that sodium chloride is completely dissociated in the solution, why is this the case? All right, the reason for this is called ion pairing. When a pair of unseparated ions acts as a single particle, reducing the colligative effect. So, what we're assuming with a Van Hoff factor of 2 is that all the sodiums and all the chlorides separate from each other, widely, right? So they act like individual particles. But if the ions stay close together, there's still an ion-ion attraction here, right? So there's no reason why they wouldn't be attracted to each other. They're acting like single particles, all right? And this is going to reduce, right, how many particles you have in the solution. And if instead of acting like 2 particles are acting like 1. So your Van Hoff factor is always higher calculated than it is experimentally. When you actually measure how much the boiling point is affected by something with a Van Hoff factor of 2 or 3, it's always a little bit less. And it depends on the substance how much less.